Okay, so for question number 1, we are given energy. So I'm going to go ahead and write that down. And we want to know what is the frequency of the light that attacked this Z electron. So what I can do is I'm looking for frequency, but I know a very cool equation. Frequency equals Planck's constant, or actually energy, divided by Planck's constant. So then what I can do is I can plug in my energy, times 10 to the negative 19 joules, all over H, which is 6.626 times 10 to the negative 34 joules times seconds. Okay, and that gets me approximately 9.056 times 10 to the 14 1 over seconds. So that's our frequency. And I'm going to say that equals frequency. Cool, so now that I have that value, I can go ahead and use my other equation, which is the speed of light constant, c, equals the wavelength times frequency. And I'll divide by frequency, which gives me wavelength right here. Oops. Wavelength. So now I can solve for my wavelength, which equals, that's going to be c, which is given. So 2.998 times 10 to the 8 meters per second, all over my frequency, which we just solved for. So let me duplicate that. Which is going to get me, that wavelength is going to come out to around approximately 3.313 times 10 to the negative 7 meters, because these seconds are actually gonna get canceled out when we do that. So now I have my wavelength value. I'm gonna go ahead and just erase all of this because I don't need it right now. So this equals wavelength. So now I want to understand what kind of radiation was the photon. So I'm going to go ahead and put it into nanometers, because that's usually what the UV radiation spectrum is going to be in. So meters, and then I want to cancel out meters. So I'm going to put that on the bottom. 1 meter equals 1 times 10 to the 9th nanometer. So these meters will go away. We're left with nanometers, and that's going to give us 331.3 nanometers. So like, cool. We were provided a sort of like a wavelength radiation spectrum diagram on the equation sheet, but so you could look at that and try and figure out where this guy falls in, what category he falls into. But just for the sake of this demonstration, I'm just going to pull this up. Oops, my picture went away. Okay, and you'll see that because our value is around 330, it's going to fall into the ultraviolet category. So this makes this ultraviolet. Okay, moving on. What was the binding energy or work function of the metal which tried to hold on to Z in units of joules per electron and then kilojoules per mole? So there's going to be a couple conversions that take place. But to start off with, we're going to go back to this equation. that was provided, which is the energy of a photon equals, let me see, this potential energy plus this kinetic energy. Okay, so what we know is that we have the E photon and we have the kinetic E, or the kinetic energy of the electron. So I'm going to go ahead and rearrange this equation. So potential energy is on that side. And then that, we subtracted that kinetic energy, so it's going to be minus the kinetic energy electron. So this potential energy is equal to E photon, which was given in the beginning, times 10 to the negative 19 joules, minus Ke electron, which we go all the way to the top, was also given, 2.0 times 10 to the negative 19 joules. And if we plug that into our calculator, this comes out to be 4.0. And I had to calculate these ahead of time because it would take me too long. So, but that's what you get. That's what I got when I plugged it into the calculator, or around that. Joules. So that's going to be that value in joules. So then we're thinking, okay, we need to figure out the work function. We got it in joules. We also want it in kilojoules now. So I'm thinking, okay, I need to get it, I need to get moles involved. So what I can do is I can use Avogadro's number, which is also provided, and I'm going to get that, I'm going to be able to convert things into moles. So that'll be very helpful. So what I'm going to go ahead and do is, it's possible to pause this. What I'm going to go ahead and do is, it's fine. I'm going to take this value, which is in joules, and I'm going to multiply it. Okay, because this is actually, what this is really saying is joules over electrons. And I want to get rid of the electrons. So what I'm going to go ahead and do, because this is joules per electrons, I'm going to go ahead and put my electrons on the top. So this is like my things. So I have this many electrons or things. Electrons. I can cancel those electrons actually, and what I'll be left with is joules over, I should be better about this, moles. That's gonna get me, I'm gonna just write this down. This is joules per electrons. Joules per electrons. Okay, so when I plug that into my calculator, I got a value that was around this number. Running out of space here. And back to our units, this was joules over moles. Okay, so I'm going to go ahead and erase this. And I'm just going to write this over here so I have it. Okay, so this was the binding energy in units of, well, right now we're in joules per moles, but I now need to convert it into kilojoules per mole. So what I know is I have joules per mole on the top, and I know that I can go ahead and convert those joules. So I'm going to get rid of them. I'm going to put them on the bottom. So I have 1,000 joules into 1 kilojoule. These go away. And this is going to get me around, we can approximate, that's going to get me around 240.9 with our sig figs. Per mole. So, just to recap, we got our binding energy in terms of units of joules per electron, and then we were able to use Avogadro's number to get that into joules over moles. And then lastly, we got it into kilojoules per mole, so which was what we wanted. Kilojoules per mole. Okay, so now moving on. So after getting expelled from the metal home it had known, Z continued moving along. What is Z's de Broglie wavelength in nanometers? So back to what we know that the mass equals 9.11 times 10 to the negative 31 kilograms. Okay, and now I'm thinking, I'm going to go to that de Broglie equation, and I know that that wavelength is equivalent to Planck's constant all over the mass times velocity. Oops, I should make my velocity and my frequency look different. So now I'm thinking, okay, I have my mass, I know Planck's constant, and I need wavelength, but I don't know velocity, so how can I find velocity? So the little hint here is that it has the same kinetic energy. And luckily, we have a formula that relates, that involves kinetic energy and velocity. So what I know is that if I go to my equation sheet, I know that kinetic energy equals 1/2 mv squared. Okay, yeah, it's listed here. So it's listed on the equation sheet as kinetic energy, oops, I have to charge this, 1/2 mv squared. And I know Ke. So I can go ahead and I'm going to isolate for velocity. So let's see. So 2Ke equals mv squared divided by m divided by n. I'm going to get square root. Kind of being lazy here, sorry. I'm going to take the square root of 2 Ke all over my mass equals velocity. Okay, so I've rearranged it to solve for velocity, which is nice. I'll write this up. Not the neatest, but you get the point. So now we can go ahead and solve for velocity. So what I'm going to do is I'm going to do the square root of 2. Ke is given. Let me write this a little bit neater. Let me see. Same kinetic energy. I forgot that value. Where was it? Okay, Ke is given. So the square root 2 times 2, oops, 2.00 times 10 to the negative 19 joules all over the mass which was given. pretend this is all under one big giant square root. And then that was approximately, that gave me around 6.626 times 10 to the 5th, and then of course we have our meters per second. You can figure out that unit, or you can just remember that it's meters per second. Okay, so I'm going to go ahead and erase this just for the sake of space. And I'm going to go ahead and put our velocity over here. So now we have all the parts that we need to complete this problem. So wavelength equals Planck's constant, which is h, which was on the equation sheet, which is 6.626. I'm sorry, I'm going to write the rest of this. Okay, Planck's constant all over the mass. And it's good practice to put parentheses around everything. But I don't always. Shrink this. Okay, so now we have our equation. And we plug that into the calculator. Let me write this. When I plug that into the calculator, and this is still in meters, so we have to remember that gave me a value of, or I'm just going to say it was around 1.10 times 10 to the negative 9 meters. So we wanted it in nanometers. So I'm going to erase this, and I'm going to do the same thing I did up above, where I used a conversion. So I want to get rid of meters, so I'm going to put 1 meter on the bottom. I'm going to do 1 times 10 to the 9th nanometers on the top, which gets me, when I plug that into my calculator, it gets me 1.10 nm. And you don't even really need to put that into the calculator. You can just see that these kind of cancel each other out. And so you would just be left with 1.10 nanometer. So, not too bad of a number. I'm going to stop the video here and charge my iPad and take the second video. Okay.